So you were, I'm sure, delighted to be here getting your money's worth for your education. Okay, so our theme has been the stuff you weren't sure you knew or weren't sure you wanted to know about all of these reactions you've been learning. We're going to start, I think last time we finished on epoxidation and the strange butterfly mechanism. Today we're going to talk about addition to carbonyls, and of course you know a lot of that from undergrad organic chemistry, so I'm going to focus on details that probably weren't covered then. And the first comes from a couple of crystallographers, Berge and Dunitz, at the ETH in Zurich. That's a research institute in Switzerland. If you want to sound cosmopolitan, you can call it the ETH, because apparently that's how you say it if you speak German. In any case, these guys were crystallographers, and they started to analyze small molecule crystal structures. And in particular, they were looking at examples where within the same molecule you had an atom that could be an electron donor, and then a carbonyl that could be an electron acceptor. So here's an example. You've heard of methadone, which I think is, what do they give you that when you're trying to overcome heroin addiction or something like that? In any case, it's got this tertiary nitrogen. Is that tertiary? No, not quite. I'm struggling to see. No, it is. 1, 2, 3 methyl groups, or 3 alkyl groups. And that nitrogen is really, really close to this carbonyl oxygen. And in fact, if you measure that distance, it's about 2.8 angstroms, which is getting on the close side of maybe actually being a bonding interaction. And then, interestingly, the angle between this nitrogen and the carbon-oxygen bond is about what you'd expect for a tetrahedral angle. So it almost looks like this molecule is wanting to, well, it almost looks like this molecule is on the way to becoming sp3 hybridized here with a tetrahedral intermediate, where this atom in blue would be bonded to the carbon that's highlighted in pink. So they sort of wondered, is that, I mean, there's not a bond and that carbon's still sp2 hybridized, though you could go in and measure the bond angles, and there's probably a little bit of pyramidalization of that carbon. It's probably not completely flat. But the question was, is what we're seeing here in this crystal structure reminiscent of the way an approach to an addition to carbonyls would occur? That is, in carbonyl addition reactions, does the nucleophile prefer to come in via this trajectory? And the question is, well, why would that be the case? So here are some calculations I did in Gaussian more than a year ago. This is NBO analysis, which, as you recall from your computational assignment, treats the molecular orbitals as though they are localized between bonds. And so you can see the individual sigma bonding orbitals, the pi star antibonding orbitals, you can see the lone pairs. So I'm showing on this image the pi star of the carbon-oxygen double bond. And notice how that pi star is angled back away from the carbon-oxygen pi bond, almost exactly at the appropriate angle for where this nitrogen is. In other words, the pi star is oriented backwards, just ready for something to attack along that trajectory to generate a tetrahedral intermediate. And then you can see how that pi star overlaps in space. This darker blue region indicates the place where the lone pair on the nitrogen overlaps with the pi star on the carbonyl. So this angle that was found in these crystal structures is called the Berge-Dunitz angle, and it's thought that when a nucleophile approaches a carbonyl, most often it does so along that trajectory because that's where the pi star is. Another example that they found was this molecule protopine, which has a large, I can't remember how many atoms are in this ring, but you have a carbonyl and a nucleophile on the other side of the ring. Again, a trialkylamine. Again, the distance is close enough to maybe be kind of a bonding interaction. Again, the angle is close to the tetrahedral angle if you talk about the angle between carbon and nitrogen versus carbon and oxygen. And again, if you do the calculations in the NBO analysis, you can see that that lone pair is overlapping extensively with the pi star. So the take-home message here is that as a nucleophile approaches a carbonyl group, it does so at the so-called Bürgi-Dunitz angle because that's where the pi star is. And it's also interesting that it approaches along an angle that's similar to what the angle is going to be in the tetrahedral intermediate. So you will hear that from time to time. And so just be aware of it. When we talked about the N to pi star interaction back in when we talked about non-covalent interactions, the fact that one of the atoms was sort of at the Bürgi-Dunitz angle with respect to a carbonyl was evidence that there was something going on there with the orbitals. Okay, anything you want to ask about that? Yeah, go ahead.
So if you can basically block the other side approach, essentially, the nucleophile with like the one just there behind the carbonyl, you can force essentially a stereochemistry.
Could you, yeah, if you can block one side, can you force addition from one side of the carbonyl versus the other? Yeah, and we're actually going to talk about that in just a little bit, about how to think about whether we add from the top face versus the bottom face. Of course, if the molecule doesn't already have a stereocenter in it, the top and the bottom faces are going to be at least an antiotopic, maybe homotopic, and in that case, you have to get a 50-50 mixture. But if there's a stereocenter, the two faces are diastereotopic, and one can be better than the other, and we're going to talk about how to deal with that. Other questions? Okay, so couple of things about carbonyl additions. We're not probably going to spend a huge amount of time on this because a lot of it is stuff that you probably already know. The classic first carbonyl addition that they teach you as an undergrad is called cyanohydrin formation. This is addition of CN- to a carbonyl. I thought we'd talk about this because it's just kind of interesting how tricky it is. It says that you want to use, you need something with a carbonyl in it, usually an aldehyde or a ketone. You need CN- as the nucleophile to add to the carbonyl, and then you need an acid to protonate the tetrahedral intermediate to get you, the product, which is called a cyanohydrin, presumably because you have the cyanide and the hydroxyl group there. You got to be careful with the acid you choose. It needs to be strong enough to protonate the tetrahedral intermediate, but you don't want to protonate CN-. Anybody know why? HCN is a lethal gas. So, and it smells like almonds, presumably, and I think by the time you smell the almonds, you're almost dead. So if you smell almonds, get the heck out of the hood, close the hood, walk away. I thought there was some data in the text that I thought was interesting. The rate of addition to the aldehyde, or rather the equilibrium constant, I'm sorry, this isn't rate, it's equilibrium constant, because the reaction is an equilibrium. So if you start with this benzaldehyde, what is that equilibrium constant? Well, for the aldehyde, it dramatically favors products. It turns out that if you add the methyl group and make the corresponding ketone, for some reason I don't want to write that the equilibrium constant drops down by many orders of magnitude to the point that actually the product isn't favored over the starting materials. A couple of reasons for that could be, well, sterics, and if it's not sterics, electronics. So methyl group is maybe a little bit bigger than the hydrogen. That probably can't explain all of this difference. The other issue is how electrophilic the pi star is. If you compare having a proton there versus a methyl group there, you've got CH bonds that can be involved in hyperconjugation with the pi star, and that should make the LUMO higher in energy and therefore less easy to attack. And this just follows the trend that you probably learned about as an undergrad or in undergrad OChem, that aldehydes are generally more electrophilic than ketones. One interesting thing that I found, though, is if your ketone is in a 5 or a 6-membered ring, that will actually shift the equilibrium way more towards products. So relative to not quite as much as for the aldehyde, but still several orders of magnitude. And what's going on there is, let's see, a couple of things. You might think about, well, is there any ring strain to relieve there because you have an sp2 carbon in a 6-membered ring? It probably can't adopt a regular chair. On the other hand, in a 6-membered ring, 120-degree angles are just fine. So there's probably not a huge amount of ring strain that's relieved when you go from sp2 to sp3 there. Let's sort of draw the chair and get a sense for the issues that are on the table. So one reason why products might be so much more favored for the 6-membered ring has to do with an eclipsing interaction between this neighboring CH bond and this carbonyl. And of course, there'd be another one on the other side. If we look down, I can't resist. I always waste class time on this, but it's just habit. All right. If we look down that carbon-carbon bond and see what we would observe, here's the CH bond that's equatorial, here's the axial one, there's the rest of the ring, and then here is the carbon-oxygen pi bond, double bond, and it turns out there's about a 4-degree angle in between those two. So they're basically eclipsed. And when you have a nucleophile like Cn- add to the pi star, you relieve that eclipsing interaction now. Though we should point out that you take something that wasn't axial and you make it axial. So you've got a couple of issues here. You've got in the product 1,3 diaxial interactions, but then you have in the starting material this eclipsed interaction. It's thought that the eclipsed interaction is worth about 4 kilocalories per mole of destabilization, whereas a 1,3 diaxial interaction between, say, an OH group and these hydrogens is worth maybe 0.7 kilocalories per mole. That's what the A value is for an OH group. And so you can see when you balance these things, it's actually better to relieve the eclipsing interaction even though you introduce some 1,3 diaxial strain. Okay. So those are some of the issues to think about when considering carbonyl additions, and not only for this reaction, but for others. Are there other things you want to talk about there? Got a weird contact lens issue going on in my left eye, making it weird to see the notes. I will spare the adjustment of the contact lens in front of you. That's kind of gross. All right. So another classic addition to carbonyls is the Grignard reaction, and there's some things here that are maybe a little bit more complicated than you might have hoped. So the Grignard reaction involves some alkyl group that is bonded to a magnesium, and the magnesium is also bonded to bromide. And we have thought of this as though it were just your regular old carbanion, and then this can be the counter ion. Nevertheless, there is some covalent character there. And so even though we use it like this, it's good to remember that the metal's around, and the metal can actually influence things. So the typical mechanism that's used, especially for, say, methyl Grignard and acetone, is that the Grignard reagent delivers methyl anion to the carbonyl. You get this tetrahedral intermediate, and some people show the magnesium metal attached to the oxygen. Other people just remember that there's a counter ion present. And then there would be aqueous workup that you would do to get your alcohol. And that mechanism works fine, but there is evidence that in some cases there are other things going on. And since this class is about learning how we've oversimplified to you, I thought I would show you this complexity. You can also imagine the Grignard reaction proceeding via what's called an electron transport mechanism, or an electron transfer, sorry, not transport, but a single electron transfer mechanism. So what would this look like? Here's your carbonyl compound. Here's your Grignard reagent, and it can be bromide or chloride. This would involve an electron from, and I'm not sure how to draw this arrow. This is how your text does it. I don't necessarily like it, but it is what it is. We're not going to make a new bond between magnesium and this carbon, but rather one of the electrons in this carbon-magnesium bond is going to be transferred into the pi star of the ketone. Okay? And the arrows here are just about keeping track of the electrons. So what would this look like? If we add one electron to our ketone, we now have a radical anion, which is sometimes called a ketyl anion. And then within, keep in mind that we have solvent molecules all around, and it's taken a while for these two molecules to find each other. So the single electron transport is fast, but at the same time, I mean to show the counter ion, and then the radical R group that was left behind is right there in the same solvent cage. And so at that point, what would happen is rapid recombination of the radicals to give you the tetrahedral intermediate, and then after aqueous workup, you would get your alcohol. It should have a positive charge. I'm so sorry. There we go. Okay. So what is the evidence for that? Well, occasionally you will see, you will isolate not the R group, or not the anion, but rather the anion, the alkyl group with a proton on it, which presumably you could have gotten from, I don't know, whatever else this would be. Presumably you could have gotten that by sort of radical abstraction. The other thing you will sometimes see is the result of radical coupling. And the only way you could make this product, I don't know why, maybe you isolate this product after aqueous workup, maybe not a major product, but certainly in enough amounts to detect. And the way you would get this is by a termination step where there's two radicals find each other. And so the observation rather of these two byproducts suggests that at least in some cases the single electron transfer mechanism is what's going on. Basically anything that might stabilize a radical, either here, the R radical, or the ketyl anion can promote this mechanism. So for example, if the groups on the ketone, if we had, say, a phenyl group on one of these, the radical would be stabilized by resonance. All right. Let's see. Couple other things. When you make a Grignard reagent, it's actually in equilibrium with a dialkyl magnesium species. And so it's sometimes not clear what the nucleophile is. It's fine to draw the mechanism like this. It's fine to draw it via this single electron transfer mechanism. But it's also possible that the species that's reactive is the magnesium that has two R groups on it. And then the Grignard reaction, though you would predict it's only first order in Grignard reagent and ketone, sometimes in terms of kinetics, it's second order, and that would be consistent with two equivalents of Grignard reagent being involved in the process, and it's thought that that might look something like this. So at the same time, the R group is attacking the carbonyl, and we're breaking the pi bond. Lone pairs on the oxygen reach out and bond with the magnesium, and then this R group comes back down and bonds to that magnesium. That's sort of a, let's see, 1, 2, 3, 4, 5, 6-membered transition state, which if you're going to propose a cyclic transition state, having it involve 6 atoms is a fairly reasonable way to do it. And so you still only react one Grignard reagent, but you needed 2 of them to make the thing go. That's not always the case, but sometimes in some cases the kinetics are consistent with 2 Grignard reagents being involved. We have not talked at all about organolithium reagents, but in the case of organolithium reagents, the idea of more than one equivalent being involved is almost certainly the case. Lithium tends to chelate carbanions, and you tend to generate fairly large structures, almost lithium carbanion aggregates that in many cases are the reactive species. And if you want to know more about that, Professor Hans Reich at the University of Wisconsin did a lot of research into what the relevant organolithium species were in solution. I believe he did a lot of lithium NMR, but I can't off the top of my head confirm in my brain that lithium's like NMR active. So anyway. Another common carbonyl chemistry thing that you will see is lithium aluminum hydride reduction. or LiAlH. In order to use lithium aluminum hydride, you need basically ether solvents. But even in ether, there's going to be a fair amount of ion pairing. So even though perhaps in your first organic chemistry class you ignored what the lithium was doing or ignored the counterion at all, actually it's pretty important. The reason people know this is because lithium aluminum hydride doesn't react in the same way as sodium aluminum hydride. So the counterion is actually important. The other reason is that if you try to do a lithium aluminum hydride reduction with some reagent that chelates lithium, some macrocyclic lithium receptor, if you tie up all the lithium, the reduction stops. And then if you add lithium ion back in, it picks up again. So you need the lithium to make the reaction go. It's thought that what happens is that the lithium coordinates the carbonyl oxygen and activates it. And at the same time, because of ion pairing, that lithium is going to bring the aluminum hydride reducing agent close to the ketone, and then you can do the classic addition to a carbonyl to get this reduced intermediate. And often now aluminum hydride is just Al3. Aluminum is just one row on the periodic table below boron. So this aluminum has an empty p orbital and is a pretty good electrophile. And so what likely happens is that the oxygen, the negatively charged oxygen that I'm showing chelating the lithium, can instead exchange with the aluminum to generate this species. Whoa, what the heck? Sorry. That's terrible. I'm just going to delete that entirely because we somehow lost the oxygen. So the aluminum will replace the lithium, and that makes the aluminum reactive again as a hydride delivery reagent. So now we can repeat 3 more times until the aluminum is bound to 4 different oxygens. So one equivalent of lithium aluminum hydride can reduce 4 equivalents of ketone. Now, I don't know actually whether in practice, because I've never done an LiAlH reduction, I don't know in practice whether you use a sort of sub-stoichiometric amount of lithium because one equivalent of the lithium aluminum hydride will reduce 4 equivalents of alcohol, or rather ketone, or whether you just use it excess. I don't know. And of course, at this point, if you then did aqueous workup, you can allow water to replace the alkoxides, and you'll end up with your alcohol. This may provide some insight too into why you may have learned that lithium aluminum hydride is not able to stop at the aldehyde, but rather goes to the alcohol. If you say start with an ester and you try to reduce it with lithium aluminum hydride, and the reason for that would be this intermediate, right? Imagine we've reduced an ester. Imagine we use lithium aluminum hydride to reduce an ester to an aldehyde. Look at what we've got now. We've got right close to the aldehyde a hydride that can be delivered from that aluminum right back into that carbon, and that carbon's electrophilic because it's bonded to an oxygen that has a positive formal charge on it. So it's presumably why you can't stop at the aldehyde for the lithium aluminum hydride. Okay, I think that's enough there. If you ever use lithium aluminum hydride, be careful. You have to use it under anhydrous conditions. There's a chance of starting a fire. I've never actually done it myself, so don't ask me for advice. Instead, get advice from the people that know what they're doing. That would be Professors Michaelis, Castle, Andrus, Savage have all done this reaction before. I have not. So, and I call myself an organic chemist. I had a dream last night about my PhD advisor and about some of my lab mates. It was really weird. It's been almost 20 years and I'm still... Yeah. I started at Wisconsin as a grad student in 2003, which is starting to look like almost 20 years ago, but those were good days. Okay, so let's talk about diastereo selectivity. There are a couple of ways of dealing with this. Diastereo selectivity of carbonyl additions. And the basic idea is this. If you have a stereocenter adjacent to if you have a stereocenter adjacent to a carbonyl, and I'm not actually even sure what to do here. Actually, what your text does is say, well, we have small, we have medium, and we have large. Okay? In any stereocenter, you're probably going to be able, there are going to be 4 different groups attached, and so we're talking about a stereocenter that's adjacent to a carbonyl. And the idea is if there's enough of a steric difference between the 3 groups that are attached, you might expect there to be some selectivity for whether you attack from the top face versus the bottom face. And you can see, I mean, we talked about this in chapter whatever it was, maybe it was 6, maybe it was 4, when we learned about stereochemistry, that the top face, as we approach this ketone, is not the same as the bottom face, right? If we approach this ketone as it's shown here, from the top face we would encounter the medium group, from the bottom face we would encounter the large group. And it doesn't actually matter, however you turn this carbon-carbon bond, however you rotate in whichever groups you put where, the 2 faces are going to be different. You see that? We need to justify that, okay? All right. So it turns out that if there's enough of a difference between the 3 groups attached to this stereocenter adjacent to the carbonyl, you can actually predict with a fair amount of accuracy what the major versus minor diastereomers are going to be. So let's talk about how that is. And there are 3 models presented. They each give the same answer, but the most sophisticated is the so-called Falconon model for carbonyl addition diastereo selectivity. And what we're talking about, by the way, is if we add a nucleophile to this, do we get addition of the nucleophile from above? Or do we get addition of the nucleophile from below? And just to be clear, those 2 options are diastereomers, which is why we're talking about this. If they were enantiomers, we wouldn't be able to distinguish between the 2. But because they're diastereomers, they don't have to have this. They don't have to form in the same to the same extent. So which one is it? So the Falconon model is based on electronic considerations, and the idea is this: we're going to. Oops, I've missed a chance to draw the evil Sith eyes associated with Newman projections. Anybody ever watch Seinfeld? No? All right. There's a character in it whose name is Newman, who Jerry Seinfeld hates, and therefore whenever he sees him, he says, "Hello, Newman." And I think of that every time we do a Newman projection. All right, we're looking down the carbon, the bond between the R group and the ketone. And then in the back is this stereo center. And the Falconon model says that the largest group should be anti to the incoming nucleophile. So the incoming nucleophile is going to approach sort of at the Berge-Dunitz angle, right? And so we're going to want that largest group to be anti to where the nucleophile would come in. So that's point 1. Largest group anti to incoming nucleophile. Now, why? Why should that be the case? And it's thought that it has to do with hyperconjugation. So as the nucleophile attacks, you're going to form a new sigma bond here, right? And then there's going to be starting to form a new sigma star right here. And if you place the leaving group anti to the nucleophile, I'm sorry, if you place the large group anti to the nucleophile, that will create a situation in which this bond, this whatever this bond is, can best hyperconjugate with the sigma star that's forming from the nucleophile. Okay. Should I draw that? Here's a sigma bonding orbital, and presumably as the nucleophile attacks, we would start to form a sigma star on this side that could overlap with that bonding orbital. And you can actually make similar arguments on the other side of the molecule. For example, if we oh, that's not what we wanted to do. And there we are. I've ruined everything. If we wanted to position, similarly, the sigma star from this large group bonding to the carbon on the other side of this Newman projection is going to be out here, and as the nucleophile comes in with its negative charge, it can donate electron density into that sigma star, and that's a favorable energetic effect. All right? Any questions you want to ask about that? Clear as mud. Will what depend on the group that is large?
If the sigma star of that particular group is a good receptor.
Right, it will. The question is, will this depend on whether or not the sigma star for this L group is a good acceptor? And the answer is yes. If among your groups, small, medium, or large, you have an electronegative heteroatom. Remember, carbon heteroatom bonds generally have lower energy sigma stars than carbon-carbon bonds, and the reason for that is because of electronegativity, which pulls both orbitals down, both sigma and sigma star, right? So, yes, if you have an electronegative heteroatom, you're going to want that one to be the one that's anti to the incoming leaving group, because that sigma star is going to be most stabilized by the incoming nucleophile.
So at that point, it really does not matter if it's the largest or...
Right. At that point, if there's not a lot of difference in terms of whether one's a heteroatom or not, you'll just choose the largest group. If, though, there is a heteroatom with a low-lying sigma star, you're going to put that one anti to the leaving group that's coming in. All right. So then what else? We've got two other groups to deal with. I'm trying to figure out, based on how we've drawn this, the small group, the medium group is going to be here, and the small group is going to be here. Okay. So that's if the nucleophile approaches from, as we've drawn it in this Newman projection, from the right-hand side. Now we want to consider what if it approaches from the left-hand side, and we're going to rotate around that carbon-carbon bond again to put the large group anti to the incoming nucleophile, right? And when we do that, the small group will be here and the medium group will be there. Okay, so do you see we have two different ways we can approach that have the largest group anti to the incoming nucleophile? We can either approach from the right-hand side, again, or the left-hand side. And the difference, once we set where that largest group is, the difference between the two sides has to do with what the nucleophile encounters on the way in, right? And remember, the Bürgi-Dunitz trajectory, is the nucleophile going to have to pass the small group or the large group? And it's actually going to be more favorable for the nucleophile to pass the small group. There's going to be some steric repulsion there that is much less steric repulsion if we approach from the other side. Okay, so the major product is going to be the one, and we'll suppose this is after aqueous workup. Here's the nucleophile that came in. Here's the R group. In the back, here's large, small, and medium. And if we look at that, from the side, what's that going to be? We'll have R group, nucleophile having come in from the top, OH back, and then so this is going to be the major product. And in terms of what we drew, that's up here, that's this one, which according to the Falconon model is going to be the major product. Yeah?
Okay, so just based on those like two pictures with the red arrows, we're saying on that first one, like the way you have it drawn in, is that it would be really close to the M.
Uh-huh.
Whereas on the other one, it's just closer to the S.
Right.
Okay, and so the second one is the one that happens.
Yeah, this is the better approach. This one's going to have a lower energy transition state, and therefore, because the reaction is basically irreversible, the fastest product to form wins, and that's going to be our major one. So this is a nice mixture of both electronic and steric factors. Electronic factors fix where that large group wants to be in order to be aligned with both that allows the incoming nucleophile to align with the sigma star of the carbon large group bond. And then the steric factor occurs because we know the nucleophile must approach. I think I've done this sort of, sorry. The nucleophile must approach along the Bürgi-Dunitz angle, and that's going to require it to be close to whatever this, that's going to require it to be close to whatever this group is. Okay, so step one is large group needs to be anti to the incoming nucleophile. And then step two is consider the two faces. Approach via the Bürgi-Dunitz angle over the small group is best. And then that will tell you which face you add to. Okay, so this is one technique you can use an existing stereocenter in the molecule to set the stereocenter at the adjacent carbonyl. All right. So that's a whirlwind of stuff. One last thing that doesn't require a lot of time, and then I think we'll save Baldwin's rules for next time, is the idea that for some alpha-beta unsaturated carbonyl compounds, as we learned in our molecular orbital chapter, the LUMO of this molecule is both on the carbonyl carbon and on the beta carbon. And so a nucleophile can add to the carbonyl carbon. We call that 1,2 addition. And this would be the product from 1,2 addition. 1,4 addition would be the nucleophile adds to the beta carbon, and you get this enol, which rapidly tautomerizes back to the carbonyl compound. This is why we call it 1,2 addition, because the nucleophile ends up on carbon 2, on the second atom of the alpha-beta unsaturated carbonyl compound, and hydrogen ends up on 1, whereas here the nucleophile's on 4 and hydrogen's on 1. Though in practice, that gets confusing because this is the product there, so where's the thing on 1? Nevertheless, we continue to call them 1,4 additions. We also call these conjugate additions, and some people will call these Michael additions, though I think the Michael reaction refers specifically to attack of an enolate on the beta carbon. So I taught my undergrad students that organolithiums and Grignards prefer 1,2, whereas cuprates prefer 1,4. And I basically said, you just have to memorize that. It turns out there is a principle underneath here, and it has to do with hard versus soft nucleophiles. So hard nucleophiles prefer 1,2 addition. And the reason for that is that for hard nucleophiles like organolithiums and Grignards, you have ion pairing between the counter ion and the R group, right? And that's going to make it so that the nucleophile is very close to the carbonyl. In particular, do you remember what we drew for the cyclic transition state mechanism of the Grignard reaction, where we had something like this? The fact that that the hard nucleophiles generally have concentrated negative charge, and that therefore a lot of pairing with their counter ion keeps the nucleophile close to the carbonyl group. In contrast, softer nucleophiles like thiolates, that's negatively charged sulfurs, enolates, and cuprates that have more diffuse charge on the nucleophile, they prefer to attack the beta carbon because the LUMO has a higher coefficient at that carbon. So there's, and remember that hard nucleophiles, the key thing that makes those reactions go is electrostatic attraction, whereas the key thing that makes softer nucleophiles work is orbital overlap, and there's better orbital overlap on the beta carbon. There's a higher, I guess, if you look at the numbers, there's a higher LUMO coefficient on the beta carbon. So there's your, I don't know if that muddies the water or makes it better, but if you wondered way back then why the heck we said that was the case, it has to do with hard-soft nucleophile theory. Okay, so that's it. That takes us through most of carbonyl chemistry. We're going to talk about cyclization next time, a little bit about carbenes, and then we'll move on from addition to elimination.